everyone, myself Dr. P. Vijayakumar, Associate Professor, Department of ECE. In this session, we are going to learn topic noise. So, this is an application of random variables and stochastic process. Here we will see the definition of noise and we will classify different types of noise. At the end of this particular session, you will be learning two learning outcomes. One learning outcome is understanding the definition of noise. Another learning outcome is classify different types of noise. So, we will see in detail about the noise and its classification. So, first, what is meant by a noise? So, noise is nothing but an unwanted signal. Noise is nothing but an unwanted signal which interferes with the original signal and corrupts the parameters of the message signal. So, simply noise is an unwanted signal which is going to interfere the original signal and it will definitely distort the message signal. So, because of the distortion, so it leads to an erroneous message. So, at the receiver side, the message will have so many errors because of this noise. So, generally noise waveform will be a random waveform. You can see we cannot predict this random waveform. So, at what point of time this noise is coming into picture and how much effect it is going to bring and at what frequencies it is going to disturb, everything is unknown to us, everything is random. So, we cannot exactly predict at what point this noise will get added to the signal, but we can identify the different sources of noise. So, accordingly we can take the protective measures so that we can recover the original message signal by following some restrictions. Okay, some common examples of noise is hiss sound in the radio receiver. So, whenever you switch on radio receiver or you are tuning the radio receiver, you will see some hiss sound or unwanted sound during tuning process. This is an example of a noise signal. So, when you plot, actually we hear through our ears, when you plot that noise signal through a waveform, the waveform will be something like this. It is a completely a noise signal. So, you can see here at the amplitude level, the amplitudes are random and at some time it is dominating, at some time it is showing some less effect. So, it is very difficult to predict the presence of noise and very difficult to identify at what point of time it is going to distort our message signal. And next, one familiar noise is buzz sound in the telephone conversation. When you are hearing or communicating through a telephone, you will see some buzz sound. So, that buzz sound is an example of a noise. It is of different sources, but the sound will be a buzz sound. Next, one more familiar noise we generally encounter in a communication, particularly we are talking about the noise in the communication, because this random variable and stochastic process is a basic course for communications and this noise is an important parameter in communication. So, we are mainly focusing the noises which are going to alter the communication. So, one more noise is flicker noise. Flicker noise generally we see in television receivers. So, when you are watching TV, you see some flicker noise. This is an example of a flicker noise. So, these are some different common examples of noise in communication and there are many. So, we will see one by one. So, noise in electronic and communication system originates from various physical mechanisms. So, noise can be originated from various physical mechanisms. There are different sources are there. So, we will see and we will define each and every noise. Okay. The first main noise, generally people are very much familiar, those who are those who are studying in communication, thermal noise or Johnson noise or Nyquist noise. Generally this thermal noise comes into picture whenever there is a random motion of electrons in a resistor or a conductor, we see this noise and this noise is generally termed as resistor noise or Johnson noise or thermal noise due to the thermal agitation of electrons. So, that is why this noise is also called as thermal noise. So, when you are doing an experiment in using a resistor, due to random motion of the electrons in the resistors and conductors, we can see this noise, thermal noise. Very frequently we see whenever you are doing a practical experiment in electronics or communication related, you see this thermal noise. Wherever you see a resistor, wherever you are using a resistor, so there we will get this noise, thermal noise. And this thermal noise is mathematically denoted as KTB, where K is the Boltzmann constant and T is the temperature measured in kelvins, B is the bandwidth measured in hertz. Okay. Next, short noise. Another source of noise, very predominant noise is short noise. It is generally occurring again in electronic devices due to random movement of charge carriers across the potential barriers. So, generally we see the potential barrier concepts in diodes, transistors, FETs, like this, all these devices. So, there will be a potential barrier. So, whenever there is a random movement of charge carriers due to the potential barrier, so whenever charge carriers are moving from high potential region to low potential region or high electric field region to low electric field region, so whenever there is a random movement of charge carriers, we see this short noise. Short noise is one of the predominant noise. And next noise we call flicker noise. Flicker noise, here you can see the flicker noise is inversely related to frequency. Okay. So, the more the frequency, the less the noise. The less the frequency, the more the noise. So, generally, this flicker noise is predominant at lower frequencies. So, at low frequencies, this flicker noise comes into picture. So, in the previous slide we have seen in televisions, we do see the flicker noise. So, when we are operating at lower frequency, this flicker noise is more dominating. When we are operating at high frequency, the flicker noise effect is very much negligible. So, because the relation is something like this, the mathematical relation, the power density is inversely proportional to the frequency. And one more noise generally we encounter, which is not predominant, but yes, it exists. This is called burst noise or popcorn noise. It is caused by the sudden changes in the current or voltage in the semiconductors, and it appears as a discrete burst. So, when you are operating the semiconductor devices, whenever there is a sudden change in voltage or current, generally you see this burst noise or popcorn noise. Okay. Next, the last one is transit time noise. So, this transit time noise, it arises at high frequencies, particularly this is significant at high frequency. Flicker noise we have seen, it is significant at low frequencies, and transit time noise is more dominant at high frequencies. Generally it comes into picture when the carriers to cross a device, this noise comes into picture. So, these are the different sources, I mean these are the different sources of noise or different types of noises generally we see when we are operating the electronic devices. Okay. So, the noise sources on summary we can tell that thermal noise or Johnson noise or Nyquist noise, short noise, burst or popcorn noise, transit time noise. All these noises are internal noises. So, the name internal noise means, so when you are operating the devices, only these noises comes into picture, and due to the external effect these noises will not come into picture. So, whenever you are operating a particular equipment or a particular device in a circuit, so these noises comes into picture. So, if you do not operate them, these noises not going to come into picture. Okay. And there are other noises, external noises. So, external noises means the noise coming from outside environment. Those are sometimes they are unavoidable. So, galactical noise, any earthquake noise, unnecessary weather noise or vehicles will cause some noise. All these are external noise. When you are operating a system, external noise also comes into picture. Internal noise comes into picture when you are operating a particular equipment or a particular device. Okay, then only internal noise comes into picture. External noise, some noises you can avoid. So, when you are operating a system which is far away from a noise free environment, you do not see any disturbance due to the external noise, but the noises due to natural calamities which are unavoidable. So, external noises, some are unavoidable, some we can control, and internal noise when you are operating, automatically they comes into picture. Already we have seen that, okay, thermal noise. So, let us see in detail about thermal noise. So, what is meant by thermal noise? What is meant by a resistive noise? Sometimes this is also called as John Nyquist noise. So, I already mentioned that a single statement we have seen, due to thermal agitation of charge carriers, particularly electrons, when the electrons are moving randomly in a resistor. So, due to this random motion of electrons in a resistor, a noise will be generated. That noise is generally termed as thermal noise or resistive noise. So, what is the cause for thermal noise? Why random motion happens in a resistive material? Because of the temperature and because of the fluctuations in the voltage and because of the random shape of the resistors. Resistors having a random shape and the movement of the electrons will be in random, and also due to the temperature, ambient temperature or outside temperature or any small fluctuations in the voltage is going to produce the thermal noise. So, these fluctuations exist in all resistors and conductors at any point of time. So, any equipment which is operated about absolute 0 degrees or 0 Kelvin, so these noises generally exist, okay. So, the mathematical expression or the mean square noise voltage when you are operating over a resistor and the bandwidth is, let us say, B, the mean square noise voltage is given as Vn square is equal to 4 kTRB. So, already we seen this. K is the Boltzmann constant, numerical value is 1.38 into 10 power minus 23 joule per Kelvin. T is the absolute temperature in Kelvin, R is the resistance in ohms, B is the bandwidth in hertz. And most familiar one is root mean square noise voltage. Root mean square noise voltage is generally expressed as mathematically Vn is equal to square root of 4 kTRB. Okay. Generally, when you are solving the problems related to noise, generally the parameter which is going to ask us is root mean square noise voltage. Okay. This expression is very important while we are solving the problems. So, the equivalent circuit for thermal noise. So, resistor, a series voltage. So, a voltage generator and a resistor connected in series to the voltage source. Otherwise, we can express in terms of current also. If a current source is parallelly connected to the resistor, then also it is valid. In source transformation theorem, we know that network theory source transformation theorem, a voltage device connected with the resistor in series is mathematically equal to the current source which is connected to the resistor parallelly. So, based on this concept, sometimes we express in terms of V and sometimes based on the source we express as IN. So, based on the resistor connection to the noise source. So, here IN RMS root mean square current is given as root 4 kTB divided by R. So, this thermal noise is very important noise. When you are using the amplifiers and receivers, there you use resistors. So, this is a fundamental noise which comes into picture whenever you are operating with resistors. So, this is very important in communication system design. So, resistor is a obvious component in any communication system design. So, while calculating the signal to noise ratio, the noise contributed by the resistor is going to considered as a major noise, and we will use these expressions in signal to noise ratio calculations also, and also in noise figure analysis also we use all these thermal noise concept only. Every time a noise exists in an electronic device, generally the predominant noise we assume it as thermal noise. Okay. So, along with thermal noise, there are some arbitrary noise sources. So, arbitrary noise sources, earlier we have taken specifically Thermal noise comes specifically due to random movement of the electron. Short noise comes into due to the charge carriers, difference in the potential barrier charge carriers. The short noise comes into picture. Flicker noise is very much dominant at lower frequency. There are some arbitrary noise sources which are going to generate the noise. So arbitrary noise sources are nothing but a non-ideal, unpredictable, unspecified noise signal that doesn't follow a simple or standard model like thermal, short or flicker. So they won't follow any specific process. So they generally come into picture when you are operating. So generally it represents the real world noise signals that can vary with waveform amplitude and frequency spectrum depending upon the system and environment. So in practical systems, when you are talking about the practical systems, noise can originate from multiple sources. So generally nowadays all equipments will have electrical elements, mechanical elements and some other additional elements. So the multiple sources refers to the noise can come from electrical parts or mechanical parts or environmental, due to environment. That's what we told, that it's an external noise. Even human made noise is also an external source of noise. All these noise sources are generally termed as arbitrary noise sources. So when the exact source type is unknown or too complex to model, then generally we call them as arbitrary noise sources. So it is very difficult to model sometimes a noise. Generally we assume it as a arbitrary noise source, very too complex to model them. So then we assume them as arbitrary noise sources. We will see some examples of arbitrary noise sources. So the environmental noise. Environmental noise means EMI effect, electromagnetic interference, EMC, EMI, electromagnetic interference from nearby circuits or power lines. Whenever a power line is near to our circuit, generally we encounter some noise because of this electromagnetic interference. So EMI noise, we call that as EMI noise, which can come from power lines or nearby circuit. And one more noise, arbitrary noise, switching noise. So switching noise is generally generated from transistor, digital circuits, so switching power supplies. So when you are using all these equipments like transistor, digital circuit, switching mode, power supplies, switching noise comes into picture. Next, mechanical vibrations. Due to mechanical vibrations, we see some noise and which is going to affect the sensors or electromechanical systems. And crosstalk noise. So whenever multiple channels are operated side by side, we will see the crosstalk noise. And human made noise, which comes from industries, motors or communication interference. All these sources comes under the category of arbitrary noise sources. Okay. So interpretation is, whenever there is a lower temperature, the better noise performance. So for example, if you are operating at 0 degree Kelvin, so we assume them as a perfectly noiseless device. Theoretically, practically there exists some noise, but theoretically we assume that based on the temperature parameter, when temperature is at 0 degree Kelvin, we assume them as a perfectly noiseless source. So low noise amplifier is an example. Okay. So generally low noise amplifiers are used in communication and radar receivers. So the temperature, based on the temperature we assume it as a noiseless device. Okay. So the applications of this arbitrary noise sources, where we use receiver sensitivity analysis, design of low noise amplifiers at front end in satellite and microwave communication system, and characterizing the noise performance in terms of temperature. So whenever you take the temperature parameter into consideration for analyzing the noise, there we use the concept of arbitrary noise sources. Okay. So in today's session, what we have seen is, we have defined what is meant by noise. Noise is nothing but an unwanted signal which is going to disturb the message signal. So message signal generally will have parameters, all parameters will get disturbed due to noise. So at the receiver, we cannot interpret the exact message signal because of the corrupted message signal. So we have seen the definition of noise, and we have seen types of noise. Types in the sense, we have seen different sources. What are the different sources which are going to contribute the noise? We have seen different classification like thermal noise, short noise, flicker noise, and transit time noise and popcorn noise. Along with that, we have seen some external noise sources which are originated from motors or industries, and some noises are unavoidable environmental noises. So, galactical noise, sky noise, all these are unavoidable. So, these are different sources of noise. So, in the next session, we will be seeing the parameters related to noise. So, we will use some parameters like noise temperature, noise figure, and noise bandwidth. All these parameters will help us to know how much amount of noise is present in the device, and how to calculate the amount of noise based on the parameters. We will define the mathematical relations also in the next session. Thank you.